All right, so picking up here from where we ended on part one, we are now going to continue forward from asking you to find the coding sequence as part of this DNA sequence. So we have our choices here. If we took the top strand and coded it from DNA into RNA, then we have the bottom strand, and if we coded it from DNA to RNA, it would now need to be flipped around because remember, we only are going to look at it in a 5' to 3' direction. The first one was already written down, 5' to 3'. So you would never have to write out all of these different reading frames. This is just kind of so you understand that we don't know where it's going to start. Now, if we are looking for AUGs, because like before, we only start at AUGs, without writing out all of the sequences, we can go through and find, oh, there's an AUG, and start from there. One set of triplets, two sets of triplets, three sets of triplets. Now, it's kind of nice when they have it broken out like this. We can go along and go, oh, look, there's the AUG, there's an AUG, there's an AUG. If we look on the other strand, and again, 5' to 3', it's already been flipped for you, we find another AUG over here. So to show you, there are 4 possible AUG start sites. We don't know which one is the correct one, but we have the amino acid sequence given to us. So if we were to start translating these, methionine stop. Okay, well, we could ignore that one. Then this one goes methionine, isoleucine, valine, phenylalanine. And we have to go, wait, what was the sequence we were supposed to be finding? It was methionine, lysine, threonine, isoleucine, isoleucine. So that's going to be this bottom one down here. Now notice up here, if we go methionine, isoleucine, valine, phenylalanine, when we hit this next AUG, it doesn't stop and start a new one or anything. It's just puts in a normal methionine and valine. Now, if you remember back to our midterm, I ask you for all possible ones. So in that case, this would be a possible one. This would be a possible one. There's also the possibility that one could start just from this methionine and go forward. There are certain ways that the body knows what to look for, or I guess any cell knows what to look for when it's finding its methionine. Eukaryotes and prokaryotes had different requirements, but just so you know, it would find it. We don't know yet exactly what they're looking for, but if we know that it has to start with an AUG, and we know the beginning amino acids like that was given to us in this question, we can determine where it would start within the sequence. So in this case, it starts here, AUG, and it keeps going. Now, I do want to tell you, you don't need to go through this whole thing of writing out the strands. Just think about it, because if this strand, this top strand, became this strand up here, it's already like it's written for you. Just think of that as a U, and it's just like this up here, GAAUG, GAA. Mentally change that to a UG, and you're done. You don't have to write out this whole strand. It's already written for you. Same thing on this one. This strand would get written down to CUU, and then it would be flipped. You just have to start reading that strand from this direction and think of it as UAAC. So in this case, you're looking for that AUG going this direction. Remember, always going from 5' to 3'. All right. Hoping that will help you, because when you get over to the sheet and it gives you long sequences, I don't want to find out that y'all coded all of it into RNA before translating it. You don't need to do it. Just mentally change those T's to U's and realize that it would be reading off the opposite strand. You're only going to be looking for those AUGs, or in this case, ATGs as it's written. Okay. Great, you found the start for the HA gene coding region. Here are the HA gene data the team has collected for the flu strains that they were studying. We only have information on the starts of the genes, but it might be enough to figure out what is different about each strain. So on top, they give us the typical HA RNA, and then they give strain 1. How has the HA protein produced by the new flu virus, or how is the HA protein produced by the new flu virus different from the typical flu virus? So in this case, you're going to be looking right here. There is a switch from an AAGA to AGGA. That G has been changed. Now, to realize the ramifications of this, we have to look at the coding sequence for it. Now, if we're going along here and we know that AUG is our start, you have to go back to your codon chart and find out what AAG coded for compared to what AGG codes for. I'm going to give you a minute to look at that. This is why if you have those 2 pages printed out, that codon chart is already right there in front of you. You can pause the video if you need more time, but to help you out here, they're both still methionine. Now it went from a lysine to an arginine. This is a missense or substitution mutation. Missense means that it's coding for a different amino acid. It's made a mistake, so you can think of it that way. Now the difference is if it codes for a stop codon, it's called a nonsense mutation. The message no longer makes sense at all. They told you the message, there was just a mistake along the way. One amino acid was changed. That's B. One amino acid has been changed. Everything else, the rest of the way, is still accurate. Strain 2. Now on this one, the change should be over here. Instead of being UUU, we now have UUA. Again, you can pause the video here to figure out what is different to its code. In this case, we now have everything's the same up to here when a leucine becomes a stop codon. Now this is the nonsense mutation. This message no longer makes sense at all. It's not just that they told you the message and there was a mistake, it's they told you nothing. It was truncated. The protein was shortened because this one would have kept going. We can't keep going when we hit a stop codon. Remember that there would be release factors that come in and the ribosome would fall off. So in this case, the protein is too short. It has a stop codon too early. Strain 3. I do believe it's a change over here. That CUA has become CCA. Again, pause the video if you want to work it out for yourself. Now here we have that ACU and ACC both code for threonine. It's called a silent mutation because we don't see any ramifications. There's no change to the last message that goes out. There's no mistakes. It's not nonsense. It's just the same protein output on the far end. So it would be that there is no difference. Now there's a difference in their sequences, but not in the amino acids. In strain 4, this one's change is, there is, you can see the difference. Oh, this U has been deleted here. Pause the video, figure it out. In this case, that has caused a frameshift mutation. So the U getting cut out of there. So the threonine, actually, so it's this U that was deleted. That threonine stayed the same, but then everything else from that point forward was changed, and then we hit a stop codon. So most of the time, if you have a frameshift mutation, you're going to end up with a stop codon being hit. So several amino acids have been changed and the protein is too short. So based on the information you have, which of the 4 strains is most likely to be the one causing the illness? So normally at this point, I would have you debate with your team and come up with the one that you think, strain 1, 2, 3, or 4. So I will take this moment to stop. Well, actually, I'm not sure how long this recording is. We'll pause here so that we can have some discussion about it. So tell me, which one do you think is causing the illness? Strain 1, 2, 3, or 4? You can talk about this on discussion boards, or I can post it up on the page on your individual team pages. I'll figure out which way works the best.